Welcome back. We will continue our discussion on photolithography, on various aspects of photolithography as we were continuing. In the last class we ended our discussion with essentially talking about a mask alignment. So, we have already talked about what exactly is a photo mask, what its role is, and then we talked about how to align a mask with respect to the silicon wafer, which is now coated with a photoresist layer. And then once the mask is aligned, then you essentially do the final step, that is you UV expose. I mean, you open the shutter of the UV light so that it gets the photoresist layer under the mask gets exposed, and depending on whether you have a positive resist or a negative resist, the subsequent optical degradation or upgradation of the exposed areas will result, so that you are now in a position to transfer the pattern on the mask onto the photoresist layer. So, I think we will do a quick recap. This is what you have a silicon wafer out here, then you have a oxide layer or the barrier which you have grown on top of the silicon wafer, then you have a priming layer, and on top of which the photoresist layer has been coated. Looking at the importance of the coating technique, we have discussed in rather detail the basic philosophy of the method that is adopted for coating photoresist, that is spin coating. And let me also point out that we have not discussed how the oxide layer is grown, because from the standpoint, though it is extremely important from the standpoint of material science or physics, but reality is from the standpoint of this particular course, how you really grow an oxide layer is not going to be that important. So, once you have the stuff ready in this condition, you bring in the mask. So, now probably you understand that this is a quartz glass plate, where this particular zone has a layer of a metal, maybe chromium. So, we also discussed how we go about it. So, probably initially a blank glass piece was taken, then the entire piece was coated with the same layer of chromium, and then over this area and this area probably the chromium layer has been etched out or stripped off. So, the alignment is ready. So, typically it is not like a handheld thing as we show or as we are showing in this cartoon maybe, but typically you place this mask on the photoresist layer with the help of a mask aligner, which we will talk in a little bit detail today, and then the stage is set for the UV light to shine on it. So, what happens is this particular part there is the light cannot penetrate, and the other parts it can penetrate, and consequently there is a structural change of the polymer depending on whether it is a positive or negative photoresist. Of course, the nature of change will be different, but reality is there is a structural change and this part remains intact. So, you know that if it is a positive photoresist, then this part remains intact, and these parts there is a degradation of the polymer. In contrast, if it is a negative photoresist, then well, this part again remains intact, but there is a cross linking over these areas. So, you probably now understand that if you now go in for subsequent development for this particular mask, if you have a positive resist, this is the structure you are going to obtain, and in case you have a negative resist, this is what your structure is going to look like. So, we understand up to this level, this is the oxide layer, and today we will continue our discussion from this point. So, talking about the exposure, well, it is a definite period of time over which the light is exposed on the mask. This is in a nutshell the so, you have the UV light here, and exposure means you allow the light to penetrate and fall on the mask. Now, once the mask has been accurately aligned with the pattern on the wafer surface, the photoresist is exposed to the pattern on the mask with high intensity ultraviolet light. Now, if you look at the spectral absorption of a typical photoresist, this is the type of absorption peak you will see, that it absorbs light corresponding to UV wavelength. Unlike so here you see in the visible range the absorption is nearly 0, but still there is some bit of absorption here between 400 and 500. So, that is one of the reason why you sort of do your photolithographic processing and exposure in a very specialized environment, very specialized environment. That is I do not know how many of you know about it, but typically not only maybe you have heard that there exists something called a clean room in which most microelectronic processing takes place. These are some sort of special type of rooms or specially created environments where the dust concentration is kept extremely low, but you realize why, because we have already talked that for many of the processing steps even the presence of one single dust particle is going to be pretty detrimental. But in addition to a clean room where most of the microelectronic processing is done, a photolithographic processing, particularly the photoresist coating, UV exposure and development is done in another class of room. I do not know, this can be a quiz question. What is the room called? What is the name of the room? Well, I do not know how many of you know it. It is actually an yellow room. Okay. And the reason is that this, if you think of the concept of Wibb gear, that is the constituent lights which make white light. Okay. You see violet is closest to the 400 nanometer wavelength, and red and yellow and red are closest to 700 nanometer on the other side of the spectrum. So, here if you look at the absorption curve, you see that these photoresists they shows a maximum absorption peak at around say 350, which is sub visible spectrum, or it is in the UV range. However, between 400 and 500 there is still some bit of absorption. Okay. So, now if you sort of expose, this is interesting. So, if you suppose have a photoresist coated film and you sort of handle it in a normal room where probably your incandescent lamp or a tube light is going on. So, this is white light, you have all the wavelengths between 400 and 700 nanometer. So, the wavelengths that correspond to, let us say, between 400 to 500, they sort of start reacting, or there is some bit of photochemical reaction within the photoresist layer because of the wavelengths present in white light that correspond to these wavelengths. So, you would like to have an environment, artificially create an environment where the illuminating light, because you can't work in complete darkness. So, you would like to artificially create an environment where these wavelengths are present in as minimum quantity as possible. Now, if you so in a yellow room, typically all the doors, windows, curtains, everything is sort of covered with yellow sheet, all the lights are yellow light. The intention is to sort of keep the wavelength of the visible light in the range of say 600 to 700 nanometer. So, because you see from this particular graph that at 600, beyond say 500, all these three photoresists, these are three commercially available photoresists, and I have taken the graph from Wikipedia. So, these photoresists sort of show very minimal absorption. So, the issue is that if you sort of move around with your photoresist coated wafer in white light, and you expect that or in other words, even before you sort of do a proper UV exposure, part of the photoresist will sort of cross link or degrade, and this cross linking or degradation is independent of the location of the mask. So, what happens is there is I mean eventually you will get some structure, there will be, even though you sort of expose later under a mask, this photoresist layer is not pristine, but it has already undergone some structural changes because of some photochemical, unwanted photochemical reaction of white light, of the components of white light having wavelength in this range with the sensitizer part. So, that is why most of the photolithographic steps associated with the microelectronic industry or other processes are sort of invariably performed in a yellow room. Okay. So, this is now you also know what is a photomask. So, it is essentially a patterned metal film on one side, the mask is aligned with the wafer. This we talked about yesterday of what is mask aligning, because for many applications, if you see, you actually do not need only a single pattern, you need multiple patterns. So, the first pattern is you can sort of create on the wafer, but then every subsequent pattern sort of becomes is a function of the first pattern. Yesterday we in the previous class we had an example. Suppose this is the type of structure you would like to create. So, well, the first structure, so let us say something like this, or let us say you want to create this type of a structure. If this is the projection, what is going to be the isometric? It can be something like this. Okay. On a let us say an oxide coated layer, and they are concentric. Okay. So, well, within the photoresist layer you are probably free to place your mask like this. Okay. Let us say the easiest way to go about it is that we take a positive photoresist and take a mask which has the chrome absorbing layer here. So, you get this zone. Now, if you want to create a structure on top of that which is concentric with this one, you would like to take a mask like this, probably a second mask, but now it becomes extremely important to position the second mask on the wafer with respect to the structure created in the first stage, or the or depending on the exposure that you had done in the first stage, or with respect to the positioning of the first mask on the substrate. So, you have to ensure that center of this and center of this sort of matches, only then you can get to your desired structure. So, this is very important, and this is exactly what a mask aligner does, because if you are sort of doing a sort of a simple photolithography in your lab, let us say for a non IC application, non microelectronic application, you want to create some channels for microfluidic experiments or some array of lines for adhesion experiments, it is perfectly fine. You probably will not worry too much about these aspects, but the moment you sort of start worrying about a real electronic application, invariably there will be multi-layer structures, and in order to achieve proper multi-layer structures without any degradation of quality or any sort of defects, it is extremely important that your the alignment of the mask for every subsequent layer matches exactly with the positioning of the mask of the previous layer. So, okay. So, this is what exactly is the purpose of a mask aligner. I will show you some more details. So, here for example, you can see that the first layer has created these structures, perfectly fine. You want to create something like this. So, how much you want your second structure to interpenetrate into the first structure, this is the role of the mask aligner. The third one, you want to have another structure. So, here you can see the first, second, third, fourth, how the mask aligner sort of becomes important. The other important concept, again a very simplified picture I will give, is that the what is known as the printing mode. Okay. This is very simple. We talk about a photoresist film or coating, and then we talk about the mask. This is the absorbing layer. As it turns out, now you have an UV source somewhere over here. Now, what we have not talked in any of these discussions, previous discussion before, is where do you physically keep the mask with respect to the resist layer. Okay. Now, this is an important question, where do you keep it? So, as it turns out that there can be 3 printing modes. The first one, the simplest one, is actually the contact printing mode, where you actually place your mask right on top of the photoresist layer. Okay, there is no physical gap. The second one is proximity mode or proximity printing. It is very similar to the contact mode, but in this case the mask is sort of kept a little away from the surface of the photoresist layer, and the third one is a projection printing, where it is kept at a substantial distance away, and in between you also have a lens or a condenser, and so it uses imaging optics in between the mask and the wafer. Okay. So, let us look into it in a little bit detail. This is very simple. So, you just take your mask, you just place it in direct contact with the photoresist layer. If there is no dust particle or any other defect, these two will come in pretty much conformal contact, because the mask and the film both are smooth. So, this is your mask. This is the film, things are in perfect contact. So, this is again here where you realize probably the importance of a dust free environment, because suppose if you want to sort of implement contact mode printing and then you have a dust. So, what is going to happen? The dust particle sitting on the film surface, that photoresist surface, or on the mask will prevent the two of them coming in conformal contact, and that will destroy the pattern transfer completely. So, this is a classic example where you can realize how a dust free environment is extremely important for proper implementation of photolithography. Because the mask is in contact with the resist, very high resolution is possible. This printing mode gives you the highest possible lateral resolution. However, there is a practical problem with contact printing, that is the debris. There might be some debris that get generated because of the exposure of the photoresist layer due to UV. Okay. So, as UV shines, you know that there is a structural change of the photoresist polymer layer, which can sort of integrate, cross link or disintegrate. Particularly in the cases it disintegrates, there might be some formation of some debris, and these debris sort of get trapped between. So, if there are some debris, formation of some debris, where do these debris go? They have no place to go. So, these debris might get trapped between film and the mask. So, that can eventually lead to a damage of the mask. So, that is not a very desirable thing, because mask again is a pretty expensive entity and you really do not want to use the mask only for once. Okay, so, essentially there are the operation is very simple. So, one is the contact, which is for exposure, and then separate for align. So, you place the mask on the film, you expose, then after exposure is over you physically detach the mask from the film, and the film is taken for subsequent processing. Mask with minimal amount of cleaning maybe is sort of reprocessed. Now, particularly in order to however, I mean we are, as I told you, as I am telling you repeatedly, I am giving you a conceptual picture, so that things remain understandable to you, and which is pretty much okay for the at the level which we are talking. But this is sort of, even for the contact printing, this is something the actual setup looks like. So, you have a lamp over here, then you have a cold mirror, then the shutter is here, a turning mirror, the condenser lens, and then finally the photo mask and the wafer is mounted on wafer chuck. So, this is how complicated this. So, this schematic I have deliberately included. So, this gives you some idea about how complicated the actual processing steps are, but this picture, when you look, it also tells you how simple the basic physics governing the entire thing is. The resolution of the contact printing by sort of can be estimated from the Fresnel diffraction, and which can be given as 0.7 times under root lambda into z, where z is the gap between the mask and the wafer plus the film thickness. So, this is essentially not only for we will probably realize what is the gap between the mask and the wafer in the subsequent slide plus the film thickness. So, this is simple to calculate, you know, because this positioning etcetera is not manual. So, you have an automatic positioner. So, you can calculate z and you can find out or estimate what sort of diffraction what sort of resolution you are likely to get. Now, particularly in order to overcome the possibility of a likely mask damage because of the debris, the concept of proximity printing was started getting more popular. In proximity exposure method, it is similar to contact printing, except that a small gap of let us say 10 to 25 micron is maintained between the wafer and the mask during exposure. This gap minimizes the mask damage, not fully eliminates, but minimizes the mask damage. And the resolution, however, this comes at a cost. The resolution is not as tight as you would like to or you typically get in case of a contact printing. But please realize that in industrial stage at the present moment, the present technology uses neither of contact printing nor proximity printing. So, this table sort of gives you an idea about what sort of resolution you might get as a function of the gap between the mask and the film. So, here you can see that this is the mask, this is the film. Unlike a proximity aligner where the things were in direct contact, here the two are not in direct contact. So, there is a physical gap, and this gap, as we say, as it is written in the slide, sort of varies from 10 to 30 microns, and this table sort of gives you an idea about how the resolution worsen as the gap distance increases. So, higher gap distance sort of ensures better protection of the mask against any possible debris related damage, but it comes at the cost of loss of resolution. So, let us say from a gap of 10 micron, which where the resolution in a particular case was let us say or is 1.4 1.5 close to 1.5 micron, it goes roughly all the way up to something like for 30 micron gap size, it sort of goes to 2.5 micron. So, this is how this is what is proximity printing mode. The most widely used and it also comes with its own advantage is the so called projection printing mode. Well, it completely eliminates mask damage, but that is not the only thing. So, the issue is that here you keep it at a substantial separation distance, the mask and the film are nowhere even close to contact, and there is an additional condenser lens between the two. So, an image of the patterns on the mask is projected onto the resist coated wafer, which is a few centimeters away. In order to achieve high resolution, only a small portion of the mask is imaged. Of course, if you have a wide area, then the condenser lens will sort of fail. This small image field is scanned or stepped over the surface of the wafer. I am just coming to it. Projection printers that step the mask image over the wafer surface are called step and repeat system, again something I will talk. So, essentially the idea is very simple, that you keep the mask substantially away from the from your film, and then you have a lens in the loosest form, in the simplest form you have a lens in between, so that it acts as a condenser and sort of creates an image on the film surface. Okay. But in order to have a high resolution, only a small portion of the mask is imaged. So, now if you are let us say talking about a large wafer, your technological limitation is that you, if you want to sort of use a mask for the entire wafer, your resolution is going to be lost, because you can't your lens will not be able to focus the beams of light at the appropriate location. So, what you do, you sort of use a very small section of the mask, you get the structures here, and so if you want the same structures to be repeated over the whole wafer, what can be the approach. So, suppose you want the same structure here, 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 everywhere. So, you expose it once, you get this structure. So, the easiest thing to do would be, once the exposure is done at this place. So, here is the mask, here is the lens, here is your photoresist coated wafer, So, once it is done, maybe you just sort of raster it, or you just with the help of a mechanized motor, you just shift your wafer from this location to this location and then repeat the experiment. This is exactly what it means. So, you see here you have a wafer, let us say you have, this is the photo mask, and then you do the exposure, you get the pattern once, and then if you want to reproduce the pattern, you just remove the wafer in this particular direction. So, this is actually this entire action of the wafer movement, etc., is sort of automated these days, and here is it is when it is what brings you to the concept or the entity called reticle. When an image on the photomask is projected several times side by side onto an wafer, this is known as stepping. So, this is exactly what was written in the previous slide, and I just did not go to the details. So, the idea is that you have your mask like this. So, you bring in the wafer, maybe you get your first exposure here, and then instead of removing the hardware, you allow your wafer to move mechanically in an automatic fashion to this location, and then do the same exposure. With stepper motors, that is the reason you sort of sometimes say that this is stepping, you can control this motion very accurately. Then once the second one is done, you again move it now to this location. Okay. So, it is like this. So, what it says here, when an image of a photomask is projected several times side by side on the wafer. So, here what you are doing, you have only one pattern on the mask, but you are projecting that several times. Okay. You have one pattern on the mask, but you are projecting that several times. Okay. You have one pattern and you are projecting this pattern several times. Okay. So, here is the mask, you are projecting it several times over here. So, this is a replica of the same mask pattern, and how do you project it? You do this by keeping this part of your hardware intact. So, the mask remains in place, the lens remains in place, but the photoresist coated wafer you sort of make it move. So, from here to let us say here, 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 then here, here, it is like this. So, this motion is motion in the xy direction is known as stepping. Okay. This is actually achieved, this stepping operation is achieved by a special class of motor called stepper motors, and when you use the photomask along with stepping, the same mask is typically referred to or called as reticle. Okay. Well, there is another thing, since in this particular exposure mode you are actually using a lens between the mask and the photoresist. So, you have an additional hardware element in comparison to proximity or contact mode printing, which is a lens essentially. In the simplest form, it is a condensing lens. So, the moment you use a lens, you can sort of have a magnification or size reduction based on where the relative distances between the mask, lens and the film. Okay. So, that is precisely what is done. Typically, along with projection, there is also a feature size reduction that one tries to obtain, and a 5x reticle is pretty common industrially. The patterns on the 5x reticle are reduced 5 times when projected onto the wafer. So, that is a simple concept, that along with this condensing action, you also position your film, photoresist coated film or photoresist coated wafer with respect to this lens in such a fashion that you sort of achieve reduction in lateral dimension. So, if you sort of do not achieve any reduction, it can be 1x, but well there are lots of reticles available, 2x, 4x, 10x. The critical question to ask is why not higher? Well, if it is higher, then the depth of focus sort of becomes very, very poor. Okay. So, anything more than 10x is avoided. Industry standard is close to 5x. Okay. So, this we have already explained. So, I think now this makes better sense to you. So, this is a reticle and you have a lens, the reduction lens. So, maybe let us say it is a 5x one. So, whatever is the feature size, you get a 5 times reduced feature replica on the photoresist layer. You do the exposure, then once the full step is complete, the stepper sort of moves from one position to the predetermined sort of pre-programmed second position, and you repeat the same step again. So, you get another image of the same pattern on your resist layer. Okay. So, it also, I mean, these are some of the things or some of the steps you may be achieving with the, or you need to achieve with the mask aligner or the stepper. Now, there can be of course the possible misalignments. So, for example, this is a very nice example. What you want to create is structures like this. So, this is the first structure, and these are the this is the second structure. Okay. So, this one if you see over here, this is indeed the correct alignment. Okay. So, that is what exactly you want to do. This one if you see misaligned side to side. So, what has happened when you were bringing in the second mask, this is the first pattern or the area corresponding to the first exposure. So, when the second mask was brought in, instead of its center matching or coinciding with the center of the first pattern, let us say its center was here. So, what happens? This was the position, and see correspondingly this is what has happened. Misaligned rotationally, this is also very interesting. So, suppose you are using a mask which the first mask was like this, the second mask, this was the first mask, it had let us say 2 of these structures, the second mask was let us say this idea, sorry for the horrible sketch. The idea was that when you place the second mask, these two center to center distance and the center to center distance here is identical. So, when you place it, it will sort of automatically lead to 2 structures like this. But in this particular case, when you see a rotational misalignment, what has happened that when you were placing the mask, this line and this line, let us say this is line L1, this is line L2, there was a finite angle between L1 and L2. So, if this is L2, you see sort of it gets sort of twisted a little bit and you get a resultant structure like this. Misaligned top to bottom is very similar to misaligned side by side. So, instead of here the position sort of was shifted to here maybe, and consequently you got a structure like this. I will give you a minute to think of how can you get a this type of a misalignment, which is known as run out. Okay. So, any guess here you see side to side or top to bottom, you see that both the features have shifted in the same direction. Okay. Here or here, both the features have shifted in the same direction. Here also you can realize that this was the axis of the bigger structure, this was the axis of the narrower structure. So, this makes a finite angle theta between the two, and consequently you see a misalignment like this. But what can be the reason for a run out type of a misalignment? Well, it is only possible if you are using, this is important to realize now, that this type of a misalignment becomes only possible only when you are using a projection type of a printing mode, a projection printing mode. What has happened here, the positioning of the photoresist layer with respect to the with respect to the reduction lens has changed from the first exposure to the second exposure. Therefore, it did not achieve the same reduction, or the projection plane at which the sample or your layer was kept has varied due to whatever reason between the first exposure and the second exposure. So, while in the first case it has projected here, and in the second case what you would have expected a smaller mask. So, you would expect that mask with a smaller feature, you would go here, but what has happened that the layer has got shifted here. Okay. So, this is large now, and if you have two such structures, so one has sort of shifted in this direction, the other has shifted in this direction. Think over it, see the slides couple of times more and correlate it with the discussions we have already had. I think it should make sense to you. So, these are some of the possible misalignments you can have while operating a mask aligner. Now, up to this stage you can probably realize or understand that photolithography and photography you can probably draw a comparison. It is you can regard, if you regard photography of the conventional type of photography which was popular, let us say even 10 years back or 5 years back, maybe when the era of digital camera was not so popular, you can regard the photoresist coated wafer to be your film, the mask aligner or the stepper to be your camera, and the mask or the reticle is essentially the subject of the picture. So, what you do in your camera, you try to focus on something you want to take picture. So, you have a camera which is essentially the lens along with the exposure electronics, and you have a film on which the image gets produced. So, suppose you want to take a picture of one of your friend or some beautiful object what you see outside the classroom, certainly. So, what you will do, so that is the image what you want to capture. You capture it on your film plane or on your essentially that memory or the digital display what these days the present day digital cameras come up with. Forget it, I mean let us keep our discussion limited to a classical film camera, and then this is being achieved with the lens and the exposure is controlled by the shutter or whatever. So, exactly similar here, the object what you are trying to capture is the pattern on the mask. Your mask aligner or the stepper is equivalent to your camera hardware, and the photoresist layer is equivalent to your film on which you want to have your pattern. So, that I always give this to be a very simple comparison between photolithography and photography. I mean not only the names are similar, but you can actually correlate them very nicely. But in the present form photolithography, whatever we have taught, we would like to keep photolithography to a more of a binary mode. Okay. So, with sharp edges, that is 0 or 1, black or white. There is, I mean though there is something called grayscale lithography which is pretty common, pretty recent development and which can be useful at times, but typically here what you would like to have eventually after developing is a structure like this with a very high fidelity. So, this is very sharp. So, let us say this is exposed and non-exposed areas of the photoresist layer. You really do not want some exposure pattern or absorption pattern within your resist layer like this, okay, which we sort of regard as. So, if this we regard as 0 and 1, completely exposed and completely unexposed, this will, if you scale, these areas will have values between 0 and 1, which is not desirable in photolithography. So, that is where it sort of again has its distinction with a camera. Okay. There is another concept of immersion lithography, which is an extended concept of photolithography, and it is essentially aimed at enhancing the lateral resolution. I will talk about it in a little bit detail later, but what happens here is that it is an extension of the projection mode lithography, where you sort of have a lens and then you have the photoresist layer. What this suggests that so whatever we were discussing here, both these everything was in air. Okay. What this suggests that the lens or there is a liquid layer between the lens and the photoresist coating. Okay. Now, what does this liquid layer does? It essentially enhances something what is called as the numerical aperture. I will skip the details for here. So, here you can see the schematic. I mean, it is essentially this is the mechanism of a stepper. You see here that there are multiple number of similar type of structures. So, now you know this is mounted on a stepper which is capable of undergoing x and y motion in x and y direction in a controlled fashion, and then you sort of put it in a liquid reservoir, or you sort of have a liquid pool over here, which essentially enhances the numerical aperture, or the resolution is increased by a factor which is Ri times of the refractive index times of the liquid. I will deliberately skip the details. So, here you can see that firstly, by way of using projection mode reduction reticle, you could sort of achieve 5 times reduction in size, and then you would like to further enhance on the numerical aperture to achieve as small size as possible, all because of the fact that eventually you are trying to create very narrow domains. Because if you remember couple of lectures back, we did talk about what is the state of art now. i5 core processors, 30 to 40 nanometer line width. So, that is what you want to achieve. The question to ask is, you might ask that okay, if it is 30 to 40 nanometer, there should not be any problem. We just create a mask which has say 40 nanometer wide zones somehow by some electron beam or some other technique, which is possible, which can be extremely expensive, but it can be possible, and then place it in front of the UV lamp, and you sort of achieve the desired reduction in the desired size, lateral width. It is not so simple because of the fact that there is some issue I mentioned in probably in the first or the second introductory lecture, that is the diffraction of light. This is the same thing that was responsible, we regarded as responsible for the occurrence of rainbow colors on the back side of a CD, or which is essentially the origin of structural color. So, because of diffraction, what again in very simple words it means is that all the wavelengths of light. So, if you have some opening which is very small, and which is significantly smaller or comparable to the wavelengths of visible light, all the wavelengths of light, or almost none of the wavelengths of light, can sort of pass through this, because light has a wave nature. So, you really can't take a mask having any feature which is very small and can use conventional optics, let us say UV light, which has a wavelength let us say between 250 to 400 nanometer, because the light just will not pass. So, this is one of the reason why you will often find that the resolution in photolithography is diffraction limited. So, in order to overcome this, what is necessary? What is necessary is to go on searching for light source which has smaller and smaller wavelength. So, you go for something UV with even lower wavelength, which sometimes is referred to as DUV or the deep UV, or maybe things like X-ray or a synchrotronic light source. But the moment you change your conventional optics to something more sophisticated, your cost, you have to think of this, because this is something that a technique that sort of finds extreme application in industry. So, the cost implications are going to be huge. So, this is where photolithography at the present is sort of stuck up. It is trying all its level, because if you remember Moore's law, it says that every second year the number of transistors that can be placed on a chip sort of doubles. So, what it loosely means that sort of feature size is sort of reduced by a half in 2 to 3 years time. So, already there is we have reached a regime of 30 nanometer, 35 nanometer. So, maybe in 3 years time, let us say 2014, we are talking about 15 nanometer period line width. Now, the question is whether because of diffraction limitation using conventional optics, can you sort of in any way stretch photolithography to that limit, or you have to think of some other technique or some other optics. These are the critical questions that are coming up. Even you might wonder, I mean, all these listening to all this, that where is your chemical engineering knowledge going to sort of come into play. If you now think of immersion lithography, this is a classic setting. There is actually a lot of research, fluid dynamic research that goes on here. So, here is a lens, here is the photoresist layer, okay, and this is now immersed in liquid. And you now know or realize that this photoresist coated wafer is actually mounted on a stepper. So, once your exposure is done at one location, what would it like to do? Let us say this is location 1, somewhere down here is location 2. It would like to sort of, the stepper would like to move from position 1 to position 2, right. Now, the critical question to ask is, in an industrial process you would also like to optimize the time, but how fast or slow the stepper should move, because if the stepper moves too fast, there might be a meniscus failure, or the meniscus between the lens and the resist layer might get detached, because what is happening, if you sort of look back to your basic fluid mechanics concept, the no slip boundary condition is sort of valid at both the interfaces because of viscous effects and things like that. This is not the right course to go in to all the details, but in your basic fluid mechanics course I am sure you have done that. So, there is a lot of research that is going on, what can be the critical speed of stepper motion. I mean, industrially you want to sort of reduce the time for movement from one location to the other to as minimum as possible, but probably it can't be as fast as you would have probably been able to do in air, because of the issues, because now you have to really worry about the meniscus, integrity of the meniscus. So, these are concepts, or these are areas which are extremely interdisciplinary in nature, and these problems can be tackled by chemical engineering or mechanical engineering or fluid dynamic approaches. So, continuing our discussion, after your exposure is over, there is a step called post exposure bake. Post exposure bake is typically done at a temperature between 110 to 130 degrees centigrade for roughly about an hour. And then for the same kind of photoresist, for the same photoresist, I would say rule of the thumb is post exposure bake is slightly at a higher temperature than soft bake. Insufficient post exposure bake will fails to eliminate the standing wave pattern. This I will just tell you what it means. Sorry for this, sort of fails to eliminate, this will not be there, fails to eliminate the standing wave pattern. Overbaking causes polymerization and affects the photoresist development. So, overbaking at this stage, what it leads, it sort of leads to polymerization of the areas which were supposed to be dissolved away during the development stage. So, this is exactly what is suppose this is the surface of photoresist. So, this is now you have the photoresist film between, let us say, these two interfaces. This is the photoresist air interface and this is the photoresist oxide interface. So, you this particular graph, so this is the photoresist layer and you are essentially looking this way. So, this is the x axis. So, the graph actually is drawn like this. If you look here, it is drawn like this. So, this is where the light sort of falls and this is along the depth of the photoresist layer. So, what happens again is due to interference of the different wavelengths, what eventually it results is the standing wave effect on the feature. So, because of this interference, the intensity sort of varies like this, which gets replicated on the photoresist layer. So, you get to a structure like this, and however, as we have told that typically you would like to have a very sharp edge, but instead of any feature, but what you land up getting is not a feature with a sharp edge, but you get features like this, which is extremely detrimental from the standpoint of your application, and the waviness of this standing wave feature is correlated to the lambda of the light source you are using and the interference. I am not going into the details of the details of interference, but you can just have a look there as constructive. So, this is the average intensity of light, and what happens is due to constructive interference and destructive interference, some areas across the depth will get overexposed, some areas will get underexposed. This results in this type of a standing wave effect on the features. Your post exposure bake actually takes care of the standing wave effect, and because of this annealing it minimizes the standing wave type of structure. So, once post exposure is done, then the next stage or the final stage I would say is the development, which is the process step that follows. The resist exposure is done, leave behind the correct resist pattern. So, this is the stage where using a mask like this. So, this is the unexposed areas and this is the exposed areas. So, it is this stage the developer solution. So, as we told initially that every photoresist sort of comes with its own developer solution. So, suppose if it is a positive photoresist, then your developer solution will wash away these zones. In contrast, if it is a negative photoresist, the developer solution will only wash away these zones. Okay. So, this is the stage of development. There are also quite a few nitty-gritty issues associated to it. It must be understood that a good development process has a short duration, because of the fact that you are using a developer solution which ideally you would like to wash away these areas and you do not want it to affect this particular area, right. Now, the critical thing is that the developer is nothing but a okay. And if you look, these areas essentially the material is the same, it is the same photoresist, only part of the photoresist layer has gone some sort of photochemical reaction has sort of undergone some structural change. However, the material remains still the same, and the developer solution you are using essentially therefore is a solvent for this material. So, if you sort of use the developer for a very long period of time, what is going to happen, it alongside sort of dissolving these areas, it will also sort of affect this structure. So, that will sort of affect the structural fidelity or things like that. So, this is important, that a good development process has a short duration, results in minimum pattern distortion or swelling, keeps the original film thickness of the protected areas intact, and retracts the intended pattern faithfully. So, it retracts only this, it does not affect the thickness of this layer, and it does not sort of lead to any sort of distortion of the pattern. So, development is carried out either by immersion developing, spray developing or puddle developing. It is always followed by through rinsing and drying to ensure that the development action will not continue after the developer has been removed from the wafer surface. Industrially, often a spin developer can also be used, which typically uses a spin coater platform. So, a development solvent dissolves the softened part of the photoresist, transfer the pattern from the mask or reticle to the photoresist, and 3 basic steps are development, rinsing and drying. We will pick up the later part of the concluding part of photolithography in the subsequent class.